Hello everyone, Geometry Unit 2, Lesson 3 on the handshake formula. By the end of the lesson, you'd be able to determine a pattern based on a set of numbers, a real-life scenario, or potentially a picture. Let's get started. Okay, for today, the first non-linear pattern that we're going to consider for the day is called the handshake formula or handshake pattern. Take, for example, that there are 30 people at a party and everyone shakes everyone's hand. So what we can do is we can represent a single person with each of these vertices. So if there's one person at the party, clearly no segments are joining any other vertices. Therefore, there would be 0 handshakes, assuming that this person doesn't shake their own hand. If there's 2 people, we could represent a handshake with a segment connecting the 2 vertices. So there would be 1 handshake. So down here I've said if there's 1 point or 1 person, 0 handshakes. 2 points or 2 people, 1 handshake. If there were 3 people, 1, 2, 3, there would be 1, 2, 3 segments, which means that there would be 3 handshakes. With 4 people, there would be 6 handshakes. With 5 people, you could do the counting. There would be 10 handshakes. Let's look at the pattern of how this nonlinear sequence is changing. You can see with the first segment or the first point that there's 0 handshakes. We increase the number of handshakes when there is a second person added by adding 1 handshake. When there's a third person added, we add 2 more handshakes. When there's a 4th person added, we add 3 handshakes. 5th person added, we add 4 handshakes. You can see the pattern is increasing by 1 in each situation. As n increases by 1, the number of handshakes increases by 1 more than the previous. Therefore, we would get 15 handshakes. And then comes our formula. Now, this is a non-linear pattern. This is not something that is predictable with a linear function rule. The function rule for the handshake pattern is n times n minus 1 divided by 2, where n is the number of people. Now, it won't always be the number of people depending on the example and word problem. Let's look at a few in slides to come. Okay, so on the previous slide, we spoke about the handshake formula. Of course, we've got it right here, where n is the number of people or objects. So we would multiply n times n minus 1, divide by 2 to get any output or function value based on the number of points present. So let's take 4 points present and let's use the formula. So n would equal 4. Therefore, f of 4 would equal 4 times 4 minus 1 divided by 2. Well, 4 minus 1 is 3. Therefore, the 4th term in this sequence would be 4 times 3 divided by 2. That's 12 divided by 2, which, look at that, is 6. So what would be f of 30? Let's find the 30th term. F of 30 would equal 30 times 30 minus 1 divided by 2. Well, f of 30 would then equal 30 times 29 divided by 2. Oops, divide by 2. Well, in this case, you would likely need your calculator. So you would take 30 times 29 and divide it by 2. Looks like at a party with 30 people, there would be 435 handshakes. Okay, now looking below, you can see that anytime you have a group of objects and each object must be connected to every other object, you can count the number of connections by using the handshake formula. Let's look at a few practical examples. Clearly, fantasy football is tops on the practical examples. So let's read the word problem and decide what we need to use here. our fantasy football team is in a league with 10 other teams. You play each team once. How many games will there be in your season? Now, it's not just for your team, but for all teams. Okay, so we're in a league with 10 other teams. So now the vertices will be number of teams, or fantasy football teams, no longer handshakes. So you can think of team number 1 over here. When they play team number 2, their matchup is kind of like a handshake. Okay, they are competing against each other. We would consider that a connection. Team number 3, when they play team number 2, that would be like another handshake. When 1 plays 3, that's another handshake, etc. All the way around to team number 11. Now you might ask, there's 10 teams. There's 10 other teams. That means that n would equal 11. So the number of games played could be represented by n times n minus 1 divided by 2. That would be equivalent to 11 times 10 divided by 2. So the number of games played within your fantasy football league would be 110 divided by 2, which is 55. Okay, let's continue with another example. All right, let's look at a different type of pattern, a visual pattern. The word concurrent means lines that intersect at the same point. So you can see I have one red line in the yellow box, but I have 2 red lines in the blue box. They are concurrent at this point, point A. I have 3 red lines in the brown box, concurrent at point B. I have 4 red lines in the orange box. They are concurrent at point C. Let's find a formula for n concurrent lines. Okay, so how many regions are created in the plane by n concurrent lines? So in the yellow region, how many different regions are formed? Well, I've got 1 region and I've got 2 regions. So that one line creates 2 regions. Okay. How about in the second box, which is the blue box? Reminds me of blue blockers. Some of you may remember that. Actually, probably none of you. There are 4 regions created. Okay, so I've got 4 regions created with 2 concurrent lines. In the brown box, with 3 concurrent lines, I get 1, 2, 3, and 4, and 5, and 6. And then with 4 concurrent lines in the orange box, I get 1, 2, 3, 4, 5, 6, 7, 8. Okay, now notice the pattern here. This is a linear pattern. And each time we create 2 more regions. When this common difference is the same, we know that our function rule will be linear. If I went back to the 0 term, if there were 0 lines, it's kind of counterintuitive. There will be 0 regions. Now, that doesn't make sense in the context of if I drew 0 lines. Would there be 0 regions? No, there'd be 1 region. But generally speaking, looking at the table, if I use this linear pattern, then our linear function rule should just be 2n. So if I had 20 concurrent lines, that would create 40 regions. Okay, let's look at another example. Let's look at a nonlinear and non-handshake pattern. So we've looked at handshake and we've looked at linear. Let's look at a non-handshake pattern. Okay, so for example, look at this rule. This rule says f of n equals n squared plus 50. So we're going to take the term number we're going to square it and then add it to 50. So f of 4 would equal 4 squared plus 50. Well, that's 16 plus 50. That's 66. Okay, f of 5, that's going to be 5 squared plus 50. Well, that's 25 plus 50, that's 75. F of 6 is 6 squared plus 50. It's 36 plus 50, that's 86. F of 7 is 7 squared plus 50. Well, that's going to be 49 plus 50, that's 99. And f of 20 is going to be 20 squared plus 50. 20 squared is 400, plus 50 is 450. Now, I notice this is not linear, right? You can see that there's no pattern to this, right? I see I'm adding, what is that, 9. And then I'm adding, what is this, 11. And then I'm adding 13. Since these values right here, these common differences are not common, therefore the pattern is not linear, and we can tell it's not handshake either. Let's look at a few more examples with handshake patterns. Okay, let's take a look at the next example. How many total diagonals can I draw in the following figures? So in a figure with 4 vertices, how many diagonals can I draw? Well, diagonal is any segment that connects non-consecutive vertices. So I could draw 2. Here, I can draw 1, 2, 3, 4, and 5. With a hexagon that has 6 sides, I could draw 2, 3, 4, 5, 6, 7, 8, 9. Now, before I start drawing a bunch for a 7-sided polygon, let's look if there's a pattern. So I'm adding 3, then I'm adding 4. I would assume that my next would be to add 5, which would be 14. Let's see if we can create 14 diagonals. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh boy. 12, 13, and there's one more I'm missing. There it is, 14, for a total of 14. Now, if I was to back this pattern up, right, and go back to 3 and 2 and 1 and 0, right, to go from the 3rd term to the 4th term, if I followed this pattern, I'd have to add 2, which would make this 0. And then I would have to add 1, which would make this -1, and I'd have to add 0, which would make this -1, and then I'd have to add -1, which would make this 0. This is a very weird pattern. This does not have a function rule. This we would just call nonlinear. So just so that we're all clear, our answers in this chapter are that a pattern is one of 3 things. It's either linear, handshake, or non-linear altogether. Now, handshake and non-linear are part of the same family. Handshake is just a special example of non-linear. And linear, of course, kind of lives in its own world where its common difference is the same in all cases. Okay, so handshake is a special formula, but it is a non-linear formula. However, there are non-linear, non-handshake patterns. Okay, let's continue. Thus, here you have it. We have either a linear function rule, which follows the form f of n equals mn plus b, or we have a handshake rule, which follows the formula f of n equals n times n minus 1 divided by 2. Let's go ahead and look at a few last examples for the remainder of the lesson. Okay, I've got a number of tables of values for a bunch of sequences here. I'd like to determine, is it linear, handshake, or neither? Okay, so as we look at the first one, we can see clearly that there's a common difference, and the common difference is 4. And that is consistent throughout the table. All right, I see that pattern happening, and it's continuing on for all values. Therefore, this would be linear. It would have a common difference of 4, and it would have an initial value, or a 0th term. If I went back to the 0th term, it would be -3, right? Because I need to add 4 to get to the first term. Okay, so I would have a -3. So my function rule here would be 4n minus 3. All right, let's look at the second example. All right, so I see a change by 1, then by 2, then by 3, then by 4, by 5, by 6, by 7. Now, this tells me this is nonlinear, so linear is out. What tells me that it would be handshake as opposed to neither? Because it's handshake. Okay, so it is handshake because we see this pattern of change, right? That we're starting at a change of 1 and increasing by a change of then 2, then 3, then 4, then 5, etc. Now, the other key, other than this pattern of change, is that the first term, when n equals 1, f of n equals 0. This is critical in order to have the handshake formula apply. Thus, the formula used would be f of n equals n times n minus 1 divided by 2. Okay, let's look at a few more. Okay, in this case, I see a change by 1, and then a change by 2, and then a change by 4, and then a change by 8, then by 16, then by 32, and by 64. Okay, so this is definitely not linear. It is not handshake, therefore it would be neither. Okay, let's continue with the next example. All right, it looks like I'm going to write anything that has a denominator of 3 with a denominator of 9. So this would be 3/9. This would be 6/9. This would be 9/9. So as I change from one to the next, it looks like I'm adding 1/9 here. I add 1/9 here. I add 1/9 to get to the next term. So it looks like my common difference is common. So I'm dealing with a linear pattern. Okay, I see that that common difference is consistent. So this will be linear. And if I went back to the 0th term and I added 1/9 to get 3/9, that would make the initial value 2/9. So the function notation for this pattern would be 1/9 n plus 2/9. Okay, our last example, let's get to it. It looks like I've got a handshake pattern going on here. Okay, I get a +1, a +2, a +3, a +4, a +5 in this pattern of change, 6 and 7. The only other thing, I know this isn't linear, the only other thing I have to check is the first term 0? Why, yes it is. This is supposed to be a thumbs up. Okay, that's a thumbs up. Therefore, that would be handshake. And we're good to go. We would use our formula, f of n equal to n times n minus 1 over 2. Key for the day, guys. If you ever have a handshake pattern, use that formula. All right, we will see you guys in the next video.